let me spend just 1 minute. So, just 1 minute for at least one acknowledgement. So, probably several of you know that our research group, the research group of machine design, was founded by Professor Paolo Lazzarini. And our group is within the larger research group conducted and directed by Professor Untitled. And in this large group, several research activities are being carried out. And this talk, I would like to say, is simply, let me say, a small further contribution in the mainstream of the large research carried out by Professor Lazzarini in the field of notch mechanics. And for instance, dealing with the fatigue effective stress definition for the fatigue stress assessment at the notches, you know that the usual approach is to obtain the strength reduction factor by the knowledge of the stress concentration factor. But since the 1977 and more strongly since 1986, Professor Lazzarini and Professor Azzori went back to the original Neuber's idea to relate the strength at point P not only to the stress field at the point P, but to the stress field surrounding the point P. And that's why many researchers coming from that group developed several theories, but almost all of them are related to that sound idea. And so, after this very large amount of investigation in mechanics of notches, is there any still open question? In my opinion, yes, at least a couple, but not so important, but someone. In my opinion, one of the questions is dealing with multi-axiality, multi-axial fatigue, and notches. So, sorry, the wrong direction. So, let us start from the usual approach. The question of this talk is, let us consider as an index of notch sensitivity the quantity Q, usually called Q. Are Q under tensile and torsion loading equal? So, more generally, is the notch sensitivity actually loading mode dependent? So, my talk will be briefly discussing this aspect. And I will consider three typical approaches developed in our larger group, let us say. That is the critical distance, the strain energy density, and the implicit gradient approach. And in critical distance approach, the sensitivity is given by the distance d, and in recent development, the distance d is loading mode dependent. Right? Sometimes. The strain energy density has a different definition, and usually the radius R is loading mode dependent. In usual approach of the implicit gradient approach, the constant C is not loading mode dependent. So, in these approaches, but first of all, the notch sensitivity is given by a distance. It's a common approach. And the distance is, and the distances are calibrated according to mechanical properties of parent material, let us say. So, first of all, is this actually a problem, the dependence of the sensitivity from loading mode? In my opinion, yes. Of course, it's a secondary problem compared to the main problem of the sensitivity, but it is a problem for two aspects. First of all, if the sensitivity is different, much more experimental data are necessary to calibrate a model. The second problem is if the notch sensitivity is loading mode dependent, critical questions arise on real components. Because often on real components, due to the complexity of the geometry, at the notches is not easy to understand which is the actual loading mode, particularly if you have multi-axial loading. Short review, probably several of you knows very well the critical distance at the strain energy density, and the implicit gradient is a more recent one. The approach is this one. You define the effective stress as a weighted average of a tensile value over a volume. This integral equation is transformed into a partial differential equation and by a proper choice of the boundary condition. We applied this approach, for instance, to several geometries and mainly welded geometries, but we applied, and this is an example carried out with Professor Taylor. I don't know if David is here. You remember well. Because tests have been performed at your lab, so you remember very well.
Yeah, we are responsible.
No, I am responsible for what I'm saying, but the job was yours. And in this case, we applied the implicit gradient with a constant value of the notch sensitivity, independently from the loading mode. And we had, in that case, good results. But more recently, myself with Professor Lazzarin and Professor Berto faced a more critical case, that is sharp notches on cast iron. And we had experimental data on simple loading, tensile and torsion, combined in-phase loading, and even combined out of phase or with different phase angles. So we had a complete set of data. And for instance, if we simply look at the strength under simple loading, let us say tension and torsion, according to the usual equation, there is a difference in the sensitivity. In this case, the strength of the notched specimen under torsion is even a little bit higher than the parent material. But this is not the only one case given in the literature. So, is it possible to check if this experimental different sensitivity are significant? Oh, we suggest a simple method. Note that this talk is not a comparison among approaches. I would like only to check if we have different sensitivities in each approach. So, we define in each approach a more monoparametric version where the distance is a constant, usually fitted under tensile, so calibrated under tensile loading, and a so-called variable distance or biparametric version of the same approach with the distance linearly dependent from, for instance, a biaxiality ratio, going from tensile to torsion loading, changing the value. We have performed the numerical analysis. I think that this part is a little bit boring. The numerical investigation has been carried out with console because the implicit gradient requires a specific built-in partial differential equation solver. And I go directly to the results. Here there are the errors of the estimations. The error of the estimations is of each approach. Errors are defined as the difference between the, let us say, the predicted and the experimental strength at 2 million cycles. So to look at this table is not so easy. This is a first graphical representation of the errors. But the final part of this talk is a discussion of the errors. I don't know if you are familiar with the analysis of variance. First of all, we can depict a distribution of errors with a so-called box plot or box and whisker plot. So in each method, let us say 1/2 of obtained data is within the box. So here you can have the scatter of the estimation for the implicit gradient from the monoparametric version to the biparametric version, and the same for strain energy density and the critical distance. This is the graphical representation. Then we perform the usual analysis of variance. The aim is to check the null hypothesis. Which is the null hypothesis? Are different? If they are, the null hypothesis is there is no different. If the data are sufficient to say that they are different, we can state that. We perform an F-test. The formulas are quite long but not so difficult. So we perform an F-test and we obtain a value. The analysis of variance states that the difference is actually meaningful, is important, if this probability of inconsistency is higher than a confidence value. Confidence value that is usually 95%. The result is that let us say, we have not enough data to say that actually results with parametric approach are different from results from monoparametric approach. So let us say difference between mono and biparametric approaches are not substantial. So this is the conclusion, and we are working on it because obviously this conclusion is related strictly to this set of data, of course. And so there are several comments where I can go directly to the final conclusion. Obtained differences are not statistically substantial, and at least it is not proved that in this set of data the introduction of a biparametric sensitivity is effective. I think that behind this there is a discussion that we can face. It is when is effective to add parameters to our model, and when is more effective to accept that there are some cases, and probably pure torsion is one of that, where our model are not able to actually depict the actual mechanical behavior of the material. And that's all.